Hello everyone and welcome back to the statistics video lecture series. Today we are going to be talking about the first of the continuous probability distributions that we will cover in this course, called the normal distribution. And we will be using the normal distribution to find probabilities. So just to kind of recap the different types of probability distributions, a probability distribution is the list of all possible values of x and their corresponding probabilities. Now, if there are a countable or finite number of outcomes, we have what's called a discrete probability distribution, and these are represented by tables or charts. If you have an infinite number of outcomes, an uncountable number of outcomes, it is called a continuous probability distribution, and these are represented by function curves. Now, the normal distribution is a special kind of continuous probability distribution. And we've actually already sort of talked about this, but we're going to talk about this in a lot more detail. So, the normal distribution is a continuous probability distribution for a random variable x. The graph of the normal distribution is called the normal curve. So, this symmetric and bell-shaped curve is also called the normal curve. And that normal distribution has a bunch of really important properties. One of them is the mean, the median, and the mode are all equal. So the mean, which is right here in the center, is also the exact center, and it is the most common occurring. So the mean, median, and the mode are all equal to that mu. Now, the normal curve is bell-shaped and symmetric about the mean. So it is in the shape of a bell, and it is symmetric about the mean, which means on either side of the mean is a line of symmetry. The right half of the graph is a perfect mirror image of the left half. That also means that area that is shaded in blue, the right half of that blue region to the right of mu is exactly equal to the shaded region to the left of the mean. Now, here's another important one. The total area underneath the standard normal curve is equal to 1. So that entire blue region there that you see shaded is equal to 1. As the normal curve approaches but never touches the x-axis, and it extends further and further away from the mean. So there really should be arrows kind of on these either sides because it can go past mu plus 3 sigma and mu minus 3 sigma. So the graph never actually touches the x-axis, it just gets forever and ever closer to it. For those of you that have taken some sort of college algebra before, it is called an asymptote. And, these right here are what are called inflection points. These are just where the graph changes from kind of curving downward to curving upward. So that one's not really that important for this course. These first 3 points are: the mean, median, the mode are all equal. The normal curve is bell-shaped and symmetric about the mean, and the total area underneath the normal curve is equal to 1. Now, the normal distribution is also informally known as a bell curve because it is bell-shaped and symmetric about the mean. The highest point on the graph is the mean, which means that this is where most of the data lies. Most of the data is going to lie right around here, right around the average. Now, the further away you get from the mean, notice how the graph is sloping downward. The further away you get from the mean, the less data there actually is. The tails, these regions here are what are known as the tails. They contain the least amount of data. So data that is less than the mean is placed to the left of the mean on the graph. So all of these right here are all data points that are less than average. All data that is greater than the mean is graphed to the right. So all of these values here are all values greater than the average. And the normal distribution can technically have any mean or positive standard deviation. And what the mean and the standard deviation are will determine the shape of the normal curve. Now, yes, they're all going to be bell-shaped, but some of them are going to be, maybe tall and skinny, and some of them might be a little bit wider. So how high they go depends on how high the average is. So the normal distribution can have any mean and any positive standard deviation. So here's just a few examples of how that same bell-shaped curve can kind of vary in shape. We have here a normal curve with a mean of 3.5 and a standard deviation of 1.5. However, if you notice for the second one, even with the mean remaining the same of 3.5, if the standard deviation is 0.7, notice how much smaller the graph is, how much more condensed it is. Remember, standard deviation is a measure of spread. The higher the standard deviation, the more spread out the graph. So with the higher standard deviation, this graph was more spread out. With the lower standard deviation, the more compact it was, which is why it looks a little scrunched. So for each of these, there are two normal curves here. We have curve A and then we have curve B. We're going to figure out which of these two curves has the greater mean and which of these two curves has the greater standard deviation. Remember, the mean is the line of symmetry right down the middle. So A's mean, the mean for graph A is right about here, and the mean for graph B is right about here. So which one has the greater mean? Well, that is curve A. A has a mean of 15, whereas B has a mean of 12. However, which curve has the greater standard deviation? That is definitely going to be curve B, because curve B is much more spread out than curve A. Curve A is much more compact and much more squished. B is much more spread out. Now, while the normal distribution can have any mean and any positive standard deviation, we have a special type of normal distribution, which is called the standard normal distribution. The standard normal distribution has a mean of 0 and a standard deviation of 1. And the horizontal scale of the standard normal curve, also known as the horizontal axis or x-axis, is going to be z-scores. So instead of labeling the x-axis with whatever the actual mean is, the standard normal curve is labeled with z-scores. And you might remember that we've covered z-scores before. We covered them back in chapter 2, and yes, it will be on this next exam as well. Z-scores are going to be a reality pretty much for this entire course. You can convert any data entry x into a z-score by using the formula z equals x minus mu divided by sigma. So the standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. And it has all of the same properties as a regular normal distribution. The total area under the curve, which is shaded here in blue, is equal to 1. And notice how this axis is labeled as z. So right in the middle, right at the mean, is a z-score of 0. Remember, the mean itself has a z-score of 0 because it is 0 standard deviations away from itself. 1 standard deviation to the right of the mean is a z-score of 1. 2 standard deviations to the right of the mean is a z-score of 2. 3 standard deviations to the right of the mean is a z-score of 3. 1 standard deviation to the left of the mean is a z-score of negative 1. 2 standard deviations to the left of the mean is a z-score of negative 2. And 3 standard deviations to the left of the mean is a z-score of negative 3. Now, when each data value in a normal distribution is converted into a z-score, a standard normal distribution is made. So we've drawn a whole bunch of those symmetric and bell-shaped curves. We did at least one for women's heights way back in chapter 2. If you were to take all of those values on the x-axis, the mean and each of the standard deviations we found, if you were to turn all of those into z-scores, you will turn your normal distribution into a standard normal distribution. Now, after you do this, the area that falls in a given interval under a standard normal curve is going to be the same as the area underneath the regular normal curve. So you also might recall the last time that we covered bell-shaped curves, we covered the empirical rule, where there is a certain percentage of the data that is going to fall between certain standard deviations of the mean. And we're just going to kind of recap that. 68% of the data is going to fall within 1 standard deviation of the mean. If you're thinking in terms of z-scores, that means 68% of the overall data is going to lie between z-scores of negative 1 and positive 1. 95% of the data is going to fall within 2 standard deviations of the mean. And in terms of z-scores, that means 95% of the data is going to be between z-scores of negative 2 and positive 2. And 99.7% of the data is going to fall within 3 standard deviations of the mean, which are z-scores of negative 3 and positive 3. Now, the empirical rule is great, but you can have a data entry, as we have seen before, lie 1.5 standard deviations above the mean. So the empirical rule doesn't really help us with cases like that. Let's say that you wanted to find the area to the left of a z-score of 1.5 or the area to the right of a z-score of 1.5. The empirical rule can't really help you with that because the empirical rule deals with data entries that have z-scores that are whole numbers. A lot of data entries, in fact, you're going to find most lie a part of a standard deviation away from the mean. So a lot of these z-scores are not going to be whole numbers. So what we have to kind of help us out with that is what is called the standard normal table. Now, the standard normal table will allow us to find the area underneath the normal curve, either below, above, or between any z-score, not just z-scores of positive -1, positive -2, and positive -3. There are some limitations because the table is only designed a certain way. So a link to the standard normal table is going to be given on Canvas. In the Canvas module that goes with this chapter, you will see a PDF titled the standard normal table. That is what I am referring to. So if you don't have that open yet, go pause this video and go open that document so that you can see it. I'm going to have some clips of, some snapshots of the table, but so that you can see the whole table, please bring that up. Now, what the standard normal table gives you is the cumulative area. Cumulative area will mean area to the left of any z-score between -3.49 and positive 3.49. So while the table only goes out to z-scores that far, you're going to find that 99.7% of the data falls between a z-score of -3 and positive 3. This one went even further than that just to make sure that almost any data value you can think of is going to be in this table somewhere. So keep in mind, though, that the standard normal curve only ever gives you the area to the left. There are ways to manipulate it to find areas to the right or between two z-scores, but they don't come directly from the table. The numbers that come directly from the table are only the areas to the left of any particular z-score. So the standard normal table has two sides. These are just snippets. These are not the complete tables, but you'll notice that there's 2 pages in that document. So there are 2 sides to this table. So we have a positive side and we have a negative side. This side here is going to be the positive side, and this side here is going to be the negative side. Now take a look at the picture. We'll start with the positive side. So if you take a look at the picture, this is a standard normal curve, and notice how it is labeled with z-scores. So each of these, what you're going to be looking up are z-scores. Now, what area underneath that standard normal curve is shaded? You might notice that the area to the left of that z-score is shaded. Like I said, the standard normal table only ever gives you the area to the left. Now, we have here z. So you're going to be looking up z-scores. Now, I will say that whenever you are finding z-scores and whenever you convert an x value into a z-score, you always need to round accurately to 2 decimal places. So the reason why we go out to 2 decimal places is because this first row here is both the ones place and the tenths place. So the number that comes before the decimal point and the first number after the decimal point are all in this column here. So we have 0.0, 0.1, 0.2. Now each of these columns here are the number in the hundredths place, so the second decimal place. So if you have a 2 in the second decimal place, you're going to be looking at this column. Now, all of these values that are in the body of the table, so you're talking this section here, all of these are areas to the left of whatever z-score you look up. So if you look up a z-score and you look into the body of the table, you will get the area to the left of that z-score. And since there are a lot of z-scores, they had to be separated. So all of the positive z-scores are on this side of the table, And all of the negative z-scores are on this side of the table. So you will notice that, here's z again. You're going to be looking up z-scores once again. Notice the area that is shaded, the area to the left of that z-score is shaded. This table only ever gives you area to the left. And then these are going to be negative z-scores. So once again, this first column here will give you the ones place and the tenths place. So we got, negative 3.4, negative 3.3, and it's going to go down. We got negative 1.9. And then how far over you go, into which column you go is the hundredths place, so the second decimal place. So if you've got a 5 in the hundredths place, you're going to go into this column. And then once again, the numbers that are in the body of the table are going to be the areas to the left of that particular z-score. Now, a couple of things to note about the standard normal distribution that you will see if you look at these tables. The cumulative area is close to 0 for z-scores of negative 3.49. So if you actually look up negative 3.49, that area right there, that area to the left, look how close to 0 that is. So it's not quite exactly 0, but it's pretty close. As z-score increases, the cumulative area increases. So, if you notice, let's look at the negative side. As the z-scores increase, as they get larger, the cumulative areas slowly get larger. The cumulative area for z equals 0 is 0.5. Yep, so if you have a z-score of 0, which is 0.00, its cumulative area is exactly equal to 0.5. Because remember, the bell curve is symmetric about the mean. The mean is the halfway point, which means half of the area is going to lie to the left of the mean, and consequently half of the area is going to fall to the right. So the area to the left of the mean itself, which is a z-score of 0, is half of the total area, which is 0.5. And I didn't have it in the snapshots, but if you look at a z-score of positive 3.49, the cumulative area is very close to 1. So what we're going to do is we are going to use the standard normal curve to find the cumulative area, which is also known as area to the left, of z-scores of 1.15 and negative 0.24. So let's start with 1.15. Well, 1.15 is a positive z-score, so I'm going to be here on the positive side. So this is the side I'm going to be looking at. Remember, all z-scores need to go out to 2 decimal places, and rounding matters because, it'll be different if you don't round correctly. So how far down I go, the row I go to, is going to be given by the number before the decimal point and the first number after the decimal point. So the ones place and the tenths place. So I am going to go down to the row that has 1.1. So I'm going to go down to right there. Now, what column I go into is going to be given by the number in this hundredths place, so the second decimal place. The number in the second decimal place is a 5, so I'm going to go to the column that has a 5 in the second decimal place. And where that row and column meet is going to be the area to the left. So that row and that column meet right there. So that is the area to the left of a z-score of 1.15. So 0.8749 is the area to the left of a z-score of 1.15. Now, if you guys want to try that on your own for this next one, feel free to pause the video. You will have to flip the table over because this is on the negative side. All right, so if you're looking up a z-score of negative 0.24, you do need to be on the negative side, which is here in the second picture. Remember, what row you go to is given by the ones place and the tenths place. So I'm going to go all the way down to negative 0.2, which is going to be that row right there. And then the column that you go into is given by the number in the hundredths place. So since there is a 4 in the hundredths place, I'm going to be going into this column right here. So where that row and that column meet is going to be right about there at 0.4052. Now, the table will only ever give you the cumulative area to the left of a particular z-score, which is really handy in a lot of cases, but sometimes you might need to find the area to the right of a z-score depending on your context. And there's going to be instances where you need to find the area between two z-scores and not just -1 and +1 or -2 and +2, etc. The table does not directly give you areas to the right or areas between two z-scores, but there is a way to very easily manipulate it so that you can find area to the right or area in between. Now, we're going to be finding a lot of we're going to be solving a lot of probability problems. We are going to have a lot of problems that say find the probability that a randomly selected whatever is either less than a value, greater than a value, or between two values. So if your probability question involves less than or some other synonym for it, what you're finding is the area to the left. So if you were finding the area to the left, the table value is your area, and you're done. If the problem involves greater than or more than or any of its synonyms, what you're finding is area to the right. Remember, the total area underneath the standard normal curve is equal to 1. So to find the area to the right, all you have to do is calculate 1 minus the area to the left, so 1 minus the table value will give you the area to the right. And then you're going to be done. So to find the area to the right, you just do 1 minus your table values, area to the left, and then that'll be it. Now, if you were finding the area between two z-scores, what you will need to do is you will need to look up both z-scores in the table. Each of those table values will be the area to the left of those corresponding z-scores. Then what you're going to do is you're going to take the bigger area minus the smaller area. So you're going to take the bigger table value, then you're going to subtract the smaller table value, and then you are done. So here's how to find areas underneath the standard normal curve. So what you need to do is, if it helps you, sketch the standard normal curve and shade the area you're supposed to be looking at. The area to the left, right, between, what are we doing? And then you're going to find the area by following the directions, and it depends on what the problem's asking. If you have to find the area to the left, then you just look it up in the table, and then that's the end of it. So if you need to find the area to the left of a z-score of 1.23, all you have to do is look it up in the standard normal table. If you look up 1.23 in the standard normal table, you get 0.8907. That is the area to the left. Now, if you need to find the area to the right of a z-score, you calculate 1 minus the table value. So let's say that you needed to find the area to the right of 1.23 instead. Well, the first thing that you do is you look it up in the table. So this is your table value, the area to the left. Then, to find the area to the right, you just subtract it from 1. So you do 1 minus your table value, and then this is the area to the right. If you need to find the area between two z-scores, what you're going to do is you're going to look them both up in the table first. So let's say you want to find this area between z-scores of 1.23 and -0.75. So you'll look them both up in the table first. So you're going to look up the area to the left of 1.23, which is a table value of 0.8907. Then you will look up -0.75 in the standard normal table, and then that will give you an area to the left of 0.2266. Then to find the area between them, you just subtract them. So you take the bigger table value minus the smaller table value, and then that will be the area in between. So we're going to practice just finding some areas first, and then we are going to then apply them to probability contexts. So what we're going to do first is we are going to find the area under the standard normal curve to the left of -0.99. So I will leave you guys to look these up, but then I will show you if or how you need to manipulate them. So we are finding an area to the left of z equals -0.99. So we have -0.99, and we are finding the area to its left. So which area does the standard normal table always give you? The standard normal table always and only gives you the area to the left. So if you were to actually look up -0.99 in the standard normal table, you will get 0.1611. And because the table gave you area to the left and the question is asking for area to the left, the table value is your area. So then for number 2, we're going to find the area under the standard normal curve to the right of a z-score of 1.06. So again, here's our standard normal table. We're going to find the area to the right of a z-score of 1.06. And I will keep saying this until you're sick of it. Which area does the table always give you? The table always gives you area to the left, and we're going to start with that. So if you look up 1.06 in the standard normal table, you get 0.8554. Let's try that again. There we go. However, this is the area to the left. To find the area to the right, you are going to subtract your table value from 1. So to find the area to the right, you're just going to do 1 minus your table value, 0.8554. And then that will give you an area to the right of 0.1446. So to find area to the right, you just do 1 minus your table value. And then for number 3, we're going to find the area under the standard normal curve between z equals negative 1.5 and z equals 1.25. So what you need to do for this is you need to look up both of them. So if you were to look up, let's say z equals 1.25 in the standard normal table, so just go look that up. The table value that goes with 1.25 is 0.8944. So that's the area to the left of 1.25. Then you are going to look up the area that goes with negative 1.5. Now remember, the table only, always goes out to 2 decimal places. So you can add a 0 to the end of this so that your z-score does go out 2 decimal places to match the table. So you're going to go down to the row with negative 1.5, and then you're going to go into the first column for negative 1.50. You should get a table value of 0.0668. If you do not, and if you're having trouble using this table, please send me an email and I will help you out. However, each of these table values are the areas to the left of their corresponding z-scores. So to find the area in between those two z-scores, you're going to subtract them. So you're going to take the bigger table value minus the smaller table value, and then that will give you the area in between, which is 0.8276. So 0.8944 minus 0.0668 gives you an area in between of 0.8276. So that is how to find areas that go with certain intervals under the standard normal curve. Tying it back to probability, remember that the standard normal distribution is a probability distribution. If you have a random variable x that is called normally distributed, when a random variable x is normally distributed, it means that it is symmetric about the mean and relatively bell-shaped. If your random variable is normally distributed, you can find the probability that x will lie in a certain interval by calculating the area underneath the standard normal curve to that interval. So what that means is you can use the areas under the standard normal curve to calculate probabilities that the value of a random variable x will lie in a certain interval. So there are going to be some variables such as, men's and women's heights that are normally distributed. So if you wanted to find the probability that a randomly selected man is less than 6 feet tall, what you can do is you can use z-scores, the standard normal table, and areas underneath the standard normal curve to find the probability that a randomly selected man is less than 6 feet tall. Now, the 3 types of intervals that we are going to be calculating probabilities for are intervals that are less than a given value, greater than a given value, and between 2 values. Remember, the total area underneath the standard normal curve is equal to 1. That's 100% in decimal form. You might remember that all probabilities need to add up to 1. That's not an accident. This is a probability distribution. So you can find the probability that x will lie in a certain interval by calculating the area under that standard normal curve for that interval. So let's say that you have, a data value of 600 and you wanted to calculate the probability that x is less than 600. Well, all you would have to do is find the area under the normal curve to the left of 600. And if you were to convert 600 into a z-score, you would be able to find the area underneath the standard normal curve by using the standard normal table. So how to find probabilities using the normal distribution can be broken down into 4 basic steps. The first step is you're not going to need to do this most of the time. But if the mean and standard deviation are not already found for you, you do need to go find them. So if you don't remember how to do this, this was back in chapter 2, so you can go ahead and watch the videos on how to do this back in chapter 2. Now, once you have the mean and the standard deviation, your probability question will involve something of find the probability that a randomly selected whatever is less than, greater than, or between a certain x. So you need to turn that data value x into a z-score using the formula z equals x minus mu over sigma. Remember, you need to do the subtraction first and then dividing. I cannot emphasize this enough. Do not use the standard normal table until you convert your x value into a z-score. So do not even touch the table until you have a z-score. You can only ever look up z-scores. So you have to turn your data entry in question into a z-score before you do anything with the table. Once you have a z-score, then you can look it up in the standard normal table. Now, after you look up your table value, you might need to manipulate it if needed, using these steps. So if your problem involves less than, or some alternatives at most, no more than, up to, fewer, smaller, below, any synonym for less than, you're going to be finding the area to the left. If you're finding the area to the left, your table value is your probability, and you're done. If you're finding the probability that x will be more than, or greater than, or bigger, at least is another really common one, or any synonym meaning greater than, you are finding the area to the right of that z-score. Remember, to find area to the right, you just do 1 minus your table value. Now, there's only so many ways to say between. So if you're finding the probability that x will be between this value and that value, you're going to be calculating the area in between those two z-scores. So yes, you will have 2 z-scores. Yes, you will have 2 table values. You're going to calculate the area in between them, which is the bigger table value minus the smaller table value. Now, again, just to emphasize, all of this depends on you finding z-scores first. So you must find z-scores first before you do any of this. Also, especially with the betweens, do not subtract z-scores. Do not subtract z-scores either from one or from each other. It doesn't work that way. You need to subtract the table value from one. You need to subtract table values from each other. Do not subtract z-scores from one, and do not subtract z-scores from each other. That is absolutely not going to get you the areas that you're looking for. These are not the areas you're looking for. Do not do this. As soon as you find the z-score, you need to look it up in the table and then manipulate the table values. So looking it up in the table should be the automatic step after finding a z-score. You can tell how many times I see people making this mistake, so don't be one of those people. Find z-score, look it up in the table, and then manipulate the table value. Please and thank you. So let's actually do one. We're going to do one, and I'm going to tell you right now, it's a less than problem. So because less than involves area to the left, the table value gives you the area to the left, which means that your table value is your probability. So let's say that the speeds of cars on a stretch of highway are normally distributed with an average speed of 35 miles per hour, so that's our mean, and a standard deviation of 2 miles per hour. We're going to find the probability that a randomly selected car is traveling less than 33 miles per hour. So in the z-score formula, your x is the data value in question. So it's the data value that's involved with the probability. So we are finding the probability that a randomly selected car is traveling less than 33 miles per hour, which means that your x value, the speed of the car in question, is 33. And we are finding the probability that x is less than 33. So regardless of whether you have a less than, greater than, or between problem, they all got to start off the same. You need to convert your x value into a z-score using the z-score formula. So I'm going to turn my 33 miles per hour into a z-score using the formula x minus the mean divided by the standard deviation. So the z-score is going to be the speed of the car in question, which is 33, minus the mean for this stretch of highway, which is 35, divided by the standard deviation for the stretch of highway, which is 2. Do the subtraction first and then dividing. Also, I don't care if the mean is bigger. It is always x minus mean in that order. Order matters with subtraction. So you're going to do 33 minus 35 divided by 2, which does give you a whole number, -1. Starting off easy. Now, all z-scores must be rounded to 2 decimal places. So if you do not have decimal places, you're going to put a couple of zeros on the end so that you can then look them up in the standard normal table. So you're going to look up -1.00 in the standard normal table. You're going to be on the negative side. Go down to the row that says -1.0, and the first column will be a 0 in the hundredths place. You should get a table value of 0.1587. Remember, which area did the table always give you? The table always gave you area to the left. We are finding the probability that a randomly selected car is traveling less than 33 miles per hour. Less than is the area to the left. So since the table gave you the area to the left and we were trying to find the area to the left, the table value is your probability. If you want to, for interpretation's sake, you can turn it into a percent if you want. So what that means is that there is a 15.87% chance that a randomly selected car is traveling less than 33 miles per hour. So let's do another one. So let's say that we have test scores in a class are normally distributed with a mean of 70, and we'll ignore the percents. We're just going to use 75, 60, etc. So they are distributed with a mean of 70 and a standard deviation of 5. We're going to find the probability that a randomly selected student scored below a 60. So remember, x in the z-score formula is the data value in question. Since this question is talking about test scores, the x value is the test score that's involved in the find the probability sentence. So find the probability that a randomly selected student scored below a 60. That means our x value, our score in question, is 60. Below is a synonym for less than. So we're finding the probability that a randomly selected student X is less than 60. So because this is a less than problem, that means that we are finding the area to the left of 60. So again, the first thing that you need to do is you need to turn 60 into a z-score using the z-score formula. So z is going to equal x minus the mean divided by the standard deviation. So the z-score is going to be the x value, the test score in question 60, minus the mean 70, divided by the standard deviation 5. And then that will give you a z-score of -2. Again, I'm making them easy at first. If you do not have numbers after the decimal point, you can just add zeros. And immediately after finding the z-score, you need to immediately look it up in the standard normal table. So you're going to go to the negative side, go down to the row that says -2.0, and into the first column for -2.00 gives you a table value of 0.0228. Because the question was asking for the area to the left, and the table value is the area to the left, that means that your table value is your probability. If you want to turn it into a percent, there's a 2.28% chance that a randomly selected student scored below a 60. So if your problem involves less than areas to the left, your table value is your probability. So I want you guys to actually try this one. It's the same test, it's the same mean, the same standard deviation. But this time, I want you guys to find the probability that a randomly selected student scored less than a 75. So I want you guys to find the probability that x is less than 75. So you'll use an x value of 75, convert it to a z-score, and find this area. So go ahead and pause the video, attempt this one, and then push play when you are ready to check your answer. Okay, so the first thing that you need to do is you need to turn your x value into a z-score. So the z-score is going to be the test score in question, 75, minus the mean, 70, divided by the standard deviation. Remember, x minus mean in that order. And then you will get a z-score of +1. I'm going to put a couple of zeros after that decimal point so that I can look it up in the standard normal table. So if you look up +1.00 in the standard normal table, you get a table value of 0.8413. Remember, we are finding the probability that a randomly selected student scored less than 75. Less than is area to the left. Since the table value gave you area to the left, the table value is your probability. So that is your probability as a decimal. As a percent, again, if you either want to or have to, there is an 84.13% chance that a randomly selected student scored less than a 75. So I want you guys to also pause the video and try this next one. So you're going to have to figure out all of the values yourself and find this probability. So go ahead, pause the video, and then resume when you are done working. All right, so let's say that a survey indicates that people get an average, also known as mean, of 2.4 years from their PCs before they have to buy a new one. And the standard deviation for that survey is 0.5 years. So mu is 2.4 and sigma is 0.5. We're going to find the probability that a randomly selected PC will last less than 2 years. So x, which is the lifespan in question, is going to be 2. And we are finding the probability that a randomly selected PCX is less than 2. So first thing we need to do is we need to turn our x equals 2 into a z-score by using the z-score formula, x minus mu in that order, divided by sigma. So the x value in question, which is 2, minus the mean, 2.4, divided by the standard deviation, 0.5, and that will actually get you a z-score of -0.8. Remember, z-scores always need to go out to 2 decimal places, so you're going to just add a 0 onto the end so that you can look it up in the standard normal table. So in the standard normal table, you're going to flip to the negative side. You're going to go down to the row that says negative 0.8. Go into the first column for negative 0.80, and that will give you a table value of 0.2119. Because this is a less than problem, what area is it asking for? Less than problems are asking for areas to the left. So since we are asked to find the area to the left, this table value was the area to the left, which means this table value is our probability. To interpret it in context, there is a 21.19% chance that a randomly selected PC will last less than 2 years. So I'm going to let you guys try this one on your own. However, I will say be extremely careful with your rounding. You need to make sure that you are rounding accurately to 2 decimal places. So go ahead and try this one, and then pause the video and then resume when you are done working. All right, so the birth weight of a breed of puppy are normally distributed with a mean of 3.3 pounds. And a standard deviation of 0.8 pounds. We're going to find the probability that a randomly selected puppy is born weighing less than 3 pounds. So the X value in question, the weight of the puppy in question is 3, so you're going to use an X value of 3. And we are finding the probability that that randomly selected puppy X weighs less than 3 pounds. So first thing we need to do is we need to turn our X value into a z-score. So we're going to turn our weight into a z-score by doing the weight in question 3 minus the mean 3.3 divided by the standard deviation 0.8. Now here's what the calculator gives you. When you do the subtraction first and then the dividing, you get negative 0.375. Excuse me. Remember, I'm going to make a huge deal about rounding because yes, I know your homework is extremely picky about rounding. Rounding is extremely important with z-scores because the table value for negative 0.37 is slightly different than the table value for negative 0.38. So you do need to make sure that you are looking up the correct one. So if you are rounding to 2 decimal places, you actually need to look at the 3rd decimal place. If that 3rd decimal place is 5 or bigger, you are going to increase the underlying digit by 1. You're going to round up. If that 3rd decimal place is 4 or less, you're going to leave it alone. So since this 3rd decimal place here is a 5, you're going to increase that 7 to an 8. So you're going to be looking up a z-score of negative 0.38. So if you look up negative 0.38 in the standard normal table, you get a table value of 0.3520. Now remember, you have to keep in mind that which area you're asked for. We're finding the probability that the puppy weighs less than 3 pounds. Less than is also known as the area to the left. Which area does the table always give you? The table always gives you the area to the left. So since we were asked to find area to the left, the table value is our probability. You can interpret this as there is a 35.2% chance that a randomly selected puppy is born weighing less than 3 pounds. So let's move on to some more than questions. Remember, if you are asked to find the probability that X is more than or any of those synonyms, you're going to do all the same steps, z-scores, table values. Then you're going to do 1 minus your table value to find the area to the right. So any more than problem will involve area to the right, which is 1 minus your table value. So let's go back to the car example. Let's say that the speeds of cars on a stretch of road are normally distributed with an average speed of 35 and a standard deviation of 2. We're going to find the probability that a randomly selected car is traveling more than 38 miles per hour. So our x value, the speed of the car in the question, is 38. And we are finding the probability that that randomly selected car is traveling at more than or greater than 38. So remember, more than is also known as the area to the right. So we are finding the area to the right of 38. It's going to start off the exact same. We need to turn 38 into a z-score first. So our z-score is going to be x, which is 38, minus the mean, 35, divided by the standard deviation, 2. So if you subtract and then divide, you get a z-score of 1.5. Put a 0 on it so that you can look it up in the standard normal table. So immediately after finding the z-score, you're going to look up the z-score in the table. So if you look up a z-score of 1.50, you get a table value of 0.9332. Now remember, which area did the table always give you? The table gave you the area to the left. So the area to the left of 38 here is 0.9332. That's not what the question is asking for. The question is asking for the area to the right, the area greater than 38. So to find the area to the right, we're going to do 1 minus the area to the left, so 1 minus your table value. And then that will give you the area to the right, which is 0.0668. So, interpreting in context, you can say that there is a 6.68% chance that a randomly selected car is traveling at more than 38 miles per hour. So that's what you do anytime that your probability question involves more than or greater than or any of those synonyms. You turn x into a z-score, look up the area to the left in the standard normal table, and then you do 1 minus your table value for area to the right. So I want you guys to actually try this one by yourself. Remember, do not subtract a z-score from 1. You're only subtracting table values from 1. So go ahead and pause the video and attempt this problem and then resume play when you are done working. All right, so let's say that the lengths of a certain breed of fish are normally distributed with a mean of 17.4. Come on, mu equals 17.4, and a standard deviation of 0.35. We're going to find the probability that a randomly selected fish measures more than 18 inches. So more than is also known as greater than. So we're finding the probability that x is greater than 18. So we're going to use an x value of 18. So remember, more than questions, this is above average. More than questions involve area to the right. So if we're finding the probability that x is greater than 18, we're finding the area under the normal curve to the right of 18. So the first thing that we're going to do is we're going to convert our x value into a z-score. So z is going to equal x, 18, minus the mean, 17.4, divided by the standard deviation, 0.35. And when you round correctly to 2 decimal places, you should get a z-score of 1.71. Then immediately after finding that z-score, you're going to look it up in the standard normal table. So if you go down to the row that says 1.7 and then to the second column for a 1 in the hundredths place, you should get a table value of 0.9564. However, that 0.9564 is the area to the left. The question is asking us to find the area to the right. So to find the area to the right, we're going to do 1 minus our table value, 0.9564, which will give us an area to the left of 0.0436. So if you want to turn this into a percent to interpret it in context, there is a 4.36% chance that a randomly selected fish is more than 18 inches in length. Now, there's only so many ways to say between, so when you're asked to find the probability that x will lie between two values, you're going to have two x values. So that means that you will have to calculate two separate z-scores, one for each x value, and you're going to have to look up both z-scores one at a time, please, in the table. Be sure to write these table values down and kind of keep track of which is which. So you're going to turn both x values into z-scores and look up both z-scores in the table. Then to find the area in between them, you do the bigger table value minus the smaller table value. And I will emphasize this again. Do not subtract z-scores. Do not subtract the z-scores from each other and then look that value up in the table. It doesn't work that way. That's not how these work. So do not do this. Please do not do this. I will laugh if YouTube makes this slide the thumbnail. Do not subtract z-scores from each other. Only subtract table values from each other. All right, so for this next one, let's say that a survey indicates that people spend an average of 45 minutes in the grocery store. So that's our mean, with a standard deviation of 3 minutes. So that's our sigma. We're going to find the probability that a randomly selected shopper spends between 37 and 42 minutes in the grocery store. So, again, in context, 37 is slightly below average, and 42 is also slightly below average. We are finding the probability that a randomly selected shopper spends between 37 and 42 minutes, which means that on the standard normal curve, we are finding the area between 37 and 42. So there are going to be two x values. One of the x values is 37, and the other one is 42. So we're going to convert both of these into z-scores first, and we are going to look up both of these z-scores in the standard normal table. So let's start with 37. So we're going to do z equals 37 minus the mean 45 divided by the standard deviation 3. Gives you a z-score. It's negative 2.6 repeating, but remember you need to round to 2 decimal places, so it rounds to negative 2.67. Then immediately after finding that z-score, you need to look up that z-score in the standard normal table. So if you go down to the, go to the negative side, go down to the row that says negative 2.6, and then over into the column that has a 7 in the hundredths place, you should get a table value of 0.0038. Then we're going to do the same thing for x equals 42. So we're going to turn 42 into a z-score first. So z equals x, 42, minus the mean, 45, divided by the standard deviation, 3. So this z-score is going to be negative 1. Throw a couple of zeros on the end, and then look up negative 1.00 in the standard normal table. So if you look up negative 1.00 in the standard normal table, you get a table value of 0.1587. Then, to find the probability that x is between these values, and in symbols it looks like this, x is between 37 and 42, you're going to be taking the bigger table value minus the smaller table value, because what's happening is you're going to get the area to the left of 42, and then you're going to subtract out the area to the left of 37, and then that will leave you with the area in between 37 and 42. So you're going to take the bigger table value, 0.1587, minus the smaller table value, 0.0038, and then that will give you an area in between of 0.1549. So that is your probability as a decimal. Interpreting this in context, there is a 15.49% chance that a randomly selected shopper spends between 37 and 42 minutes in the grocery store. So for this next one, we're going to go back to the PC example again. Company finds that people PCs last an average of 2.4 years with a standard deviation of 0.5 years. So mu equals 2.4, sigma equals 0.5. We're going to find the probability that a randomly selected PC lasts between 1.4 and 2.1 years. So we are finding the probability that X is between 1.4 and 2.1 years. So I want you guys to actually try this one. So I want you guys to pause the video, give this one a try, and then resume when you are done working to check your answer. All right, so we have two X values. One of them is 1.4. So we have X equals 1.4. And then the other X value is 2.1. So we're going to convert each of these into z-scores and look up each of those z-scores in the standard normal table. So turning 1.4 into a z-score, we have z equals x, 1.4, minus the mean, 2.4, divided by the standard deviation, 0.5, gives us a z-score of exactly -2. Put a couple zeros after it so that we can look it up in the standard normal table. So if you look up -2.00 in the standard normal table, you should get a table value of 0.0228. Then for x equals 2.1, we're going to do the same thing. We're going to turn this into a z-score by using the formula z equals x, 2.1, minus the mean, 2.4, divided by the standard deviation, 0.5. which gives us a z-score of -0.6, and then put an extra 0 after it so that we can look it up in the standard normal table. So looking up -0.6 in the standard normal table gives us a table value of 0.2743. So then, to find the probability that x is between 1.4 and 2.1, we're going to take the bigger table value, 0.2743, and we're going to subtract the smaller table value, 0.0228, and then that will give us an area in between of 0.2515. So then that will be your probability. So interpreting it in context, there is a 25.15% chance that a randomly selected PC lasts between 1.4 and 2.1 years. So this next example kind of has a combination of all of these. So for each of these parts, let's say that runners of a road race finished in an average of 36 minutes, so mu equals 36, with a standard deviation of 4 minutes, so sigma is equal to 4. So what I want you guys to do is, using this mean and this standard deviation, I want you guys to, for part A, find the probability that a randomly selected runner finished in under 30 minutes. Then for B, find the probability that a randomly selected runner finished in more than 38 minutes. And then for part C, find the probability that a randomly selected runner finished between 30 and 38 minutes. So I want you guys to go ahead and pause the video and work through each of these parts, and then resume when you are done working so that you can check your answer. All right, so we're finding the probability that a randomly selected runner finished in under 30 minutes. So we're finding the probability under, below, also known as less than, also known as area to the left. We're finding the probability that x is less than 30. So first thing we're going to do is we're going to turn 30 into a z-score. So z equals x, 30, minus the mean, 36, divided by the standard deviation, 4. Gives us a z-score of -1.50. So then you're immediately going to look it up in the standard normal table. So look up -1.50 in the standard normal table, gives us a table value of 0.0668. Now we're finding the probability that a randomly selected runner finished in under 30 minutes. Under is also known as less than. Which area is less than? That is the area to the left. Which area does the table value always give you? Table value always gives you area to the left. So since we just found area to the left and we were asked to find the area to the left, the table value is our probability. So there's a 6.68% chance that a randomly selected runner finished in under 30 minutes. For part B, we're finding the probability that a randomly selected runner finished in more than 38 minutes. More than is also known as greater than. So we're finding the probability that x is greater than 38. Which area are we asked to find here? More than is also known as the area to the right. So we're asked to find the area to the right of 38. So first, we're going to turn 38 into a z-score. So z equals x, 38, minus the mean, 36, divided by the standard deviation, 4, gives you a z-score of 0.50. So if you look up 0.50 in the standard normal table, you get a table value of 0.6915. Then to find the area to the right, remember this table value is always area to the left. To find the area to the right, you're going to do 1 minus your table value, so 1 minus 0.6915 gives us an area to the right of 0.3085. So there is a 30.85% chance that a randomly selected runner finished in more than 38 minutes. Then for part C, we're going to find the probability that a randomly selected runner finished between 30 and 38 minutes. Now, I'm not going to ask you to, find the z-scores all over again. We already found the z-scores, and we already found the table values that go with them. So the table value that went with the z-score for 38 was 0.0668. Sorry, that was for 30. So when you turn 30 into a z-score and look up that z-score in the table, you get a table value of 0.0668. And then for 38, when you convert 38 into a z-score and look it up in the table, you get a table value of 0.6915. So if we're finding the probability that a randomly selected runner finished between 30 and 38 minutes, we're going to take the bigger table value and subtract the smaller table value. So we're going to take the bigger table value, 0.6915, minus the smaller table value, 0.0668, and then that will give us the area in between, which is the probability between. So that will give us an area in between of 0.6247. Which means that there is a 62.47% chance that a randomly selected runner finished between 30 and 38 minutes. Now, in most contexts, like I'm thinking the second exam, which is what this material is going to, you're going to be tested on this material on exam 2. I'm not going to tell you whether the problem is a less than, a more than, or a between. You are going to be left to figure out whether you're supposed to find the area to the left, find the area to the right, or find the area in between. You have to figure that out. I won't tell you. So I want you guys to read through this problem, figure out what type of probability you have, figure out what area you're supposed to find, and then go ahead and find this probability using the standard normal distribution. All right, so a survey indicates that people use their cell phones for an average mean of 1.5 years before buying a new one. The standard deviation for that survey was 0.25 years. A cell phone user is selected at random. We're going to find the probability that that user will use their cell phone for less than 1 year before buying a new one, and we're going to assume that the variable x is normally distributed. So we are finding the probability that a randomly selected cell phone user uses their phone for less than 1 year. So this is a less than problem. Which area do less than problems involve? Those involve areas to the left. So we're finding the area to the left of x equals 1. Areas to the left means that your table value is your probability. So we're going to first turn our x equals 1 into a z-score by doing z equals x, 1, minus the mean, 1.5, divided by the standard deviation, 0.25, gives us a z-score of negative 2.00. Then you're going to look up negative 2.00 in the standard normal table, which gives you a table value of 0.0228. And because this was a less than problem and it asked for area to the left and the table gave us area to the left, that means our table value is our probability. Or there is a 2.28% chance that a randomly selected cell phone user uses their phone for less than 1 year before buying a new one. Now, you can think of these percentages not only as probabilities, but you can think of them as percentages of the original data. So another way to interpret this 2.28% is to say that 2.28% of all cell phone users use their phone for less than 1 year. So that's just a different way of interpreting it. Either a randomly selected user uses their phone for less than a year, or 2.28% of all users use their cell phone for less than 1 year. We're going to use that for this question. So let's say a survey indicates that for each trip to the supermarket, a shopper spends an average of 45 minutes in the store, so mu equals 45, with a standard deviation of 12 minutes. That's quite a spread. So sigma equals 12. The lengths of time spent in the store are normally distributed and are represented by the variable x. So let's say a shopper enters the store. So for each time interval listed, we're going to be doing two things. We're going to find the probability that the shopper will be in the store for each time interval listed. And then let's say that 200 shoppers enter the store. We are going to interpret those answers when 200 shoppers enter the store to figure out how many shoppers would you expect to be in the store for each time interval that is listed. So let's do the easy part first. So we're going to find the probability that the randomly selected shopper spends between 24 and 54 minutes in the grocery store. So let's convert each of our x values into z-scores. So turning 24 into a z-score, we have z equals 24 minus the mean 45 divided by the standard deviation 12 gives us a z-score of negative 1.75. Then when we look this up in the table, our table value is 0.0401. Then we're going to do the same thing for 54. So we're going to turn 54 into a z-score. So z equals 54 minus the mean, 45, divided by the standard deviation, 12. And then that will give us a z-score of 0.75. So then when you look up 0.75 in the standard normal table, you get 0.7734. So then to find the area in between them, you're going to take the bigger table value, 0.7734, minus the smaller table value, 0.0401, and then that will give you an area between of 0.7333. You can also interpret this as there is a 77.33% chance that a randomly selected shopper spends between 24 and 54 minutes in the grocery store. Here's another way to interpret that. You could also say that 77.33% of all shoppers spend between 24 and 54 minutes in the grocery store. So you can think of this as both a probability and a percentage of the overall data. Here's where the 200 shoppers part is going to come in. If 200 shoppers walk into that store, 77.33% of them will spend between 24 and 54 minutes in the grocery store. At least that's what you would expect. So to actually find that number of shoppers, what we're going to do is we're actually going to find 77.33% of 20. So we're going to take our percentage as a decimal place. So we're going to take the 0.7733. And we are going to multiply it by 200 shoppers. And since this is people, we're going to round down. We're going to round to the nearest whole number. We're going to round down to the nearest whole number. So 0.7733 times 200 gives you approximately 146. So what this would mean is that according to this data, if 200 shoppers walk into that store, you would expect about 146 of them to spend between 24 and 54 minutes in that grocery store, which is 77.33% of that 200. So I want you guys to try that for number 2. I want you guys to find the probability that a randomly selected shopper spends more than 39 minutes in the grocery store, and then use that percentage to find out of those 200 shoppers, how many of them will spend more than 39 minutes in the grocery store. So go ahead and give that one a try. All right, so let's start by finding the probability that the randomly selected shopper spends more than 39 minutes in the grocery store. So we're going to turn it into a z-score. So z equals x, 39, minus the mean, 45, divided by the standard deviation, 12. That will give us a z-score of negative 0.5, which you are going to look that up in the table first. So if you look up negative 0.50 in the standard normal table, you get a table value of 0.3085. Then since this is more than, this is an area to the right, so we're going to do 1 minus our table value for the area to the right. So 1 minus 0.3085 gives us an area to the right of 0.6915. Which means that there is a 69.15% chance that a randomly selected shopper spends more than 39 minutes in the grocery store. You can also think of this as 69.15% of all shoppers spend more than 39 minutes in the store. So if 200 shoppers walk into that store, you would expect 69.15% of them to be in there for more than 39 minutes. So to find the actual number of shoppers, we're going to take our percentage as a decimal, 0.6915. We're going to multiply it by those 200 shoppers. And then, again, whole numbers, these are people, we get approximately 138. So according to this data, if 200 shoppers walk into the store, you would expect 138 of them to spend more than 39 minutes in the grocery store, which is 69.15% of those 200 shoppers. So that is how to use the standard normal curve to find probabilities of a random variable x lying in a certain interval. We are not done with the normal distribution yet. We're going to be doing a lot more. So stay tuned for those other videos of other uses of the standard normal distribution. So thank you all very much for watching. I know this video was a little long, so thank you for bearing with it. And I will see you guys in the next video. Bye-bye.